Hello, I'm going to backdate a couple of videos 'cause I haven't gone through examples A and B for the method of joints. So I'll put this in the week 3 folder, make an announcement that it's there. So the first video I will be using the notes and making notes on top of the notes. So we're basically talking through this in a bit more detail. So that'll be the first video, and the second video I will take example B and I will do that just freestyle on the screen as a whiteboard kind of thing. Okay. So this problem, example A, they've already calculated the various reactions. So we had a load here and we had a load here. We then worked out what those reactions are. Note that we ended up with 3 reactions. Okay, that's kind of significant for when you come onto method of sections. Why you can cut through 3 members, because you expose 3 forces. Okay. So what we're going to do is we're going to start at this joint here. I've got two choices where I can start. I could either start at joint A or I could start at joint D. Because with the method of joints, you start with a joint where there's only 2 members. Usually this is where you've got some support reaction going on, and that's true in this case. If it's maybe, but that's not always the case. For example, maybe we could imagine a square like that, and that you'd have a hinge maybe here and a pivot here. In that particular case, you could start the method of joints around the hinge, or you could start the method of joints around this joint here. Okay, so it doesn't have to be necessary at the support, but normally it will be. The reason why we can only cut through 2 joints is because we've only got 2 equations to play with. We've got some in the x forces in the x direction, and some in the forces in the y direction. Why do we only have these 2 forces to play with? Because we're going to create a free body diagram based on the forces that are behaving at that joint, and because we've got no forces going from no distance away from the joint, all the forces are going through that joint. We've got no turning moment, no turning forces, so we can't sum up our moments here. So that's our only 2 equations that we've got to play with. So after I've cut around my joint, the next thing I want to do is label up those 2 members that have been cut through and make them pretend that they've now become imaginary external forces. They are internal forces that are going along the members. Okay, so the force has to travel along these members, a bit like string. Your force can't go along anywhere else. In fact, if it's a tie, it could be behaving exactly like string. But the same thing is true for a strut. If I'm applying some force at one end, it has to travel down that strut until it finds another joint to push the force against. Okay, so my convention for labeling up the forces is to use the lower letter first. I think in the course notes they tend to use the letter that you're moving away from, but since when we move on to joint B here, that would mean that you would could start confusing yourself whether I should be calling this BA or AB. So I like to use always the lower letter first when I label up my forces, and that's what we've got here anyway. Okay. So the next thing is to find out what these forces are, the values. When you're doing your method of joints, you don't have to follow convention and sum up forces in the x direction first. You could, if you want to, sum up forces in the y direction first. And sometimes it's probably the best thing to do. And it's the best thing to do in this case because you can see I've got AB, and this is now, we're saying this is now a force, and we're saying it can be broken down into two force components. A force component going in the y direction and a force component going in the x direction. Okay, so if we then got rid of this and then replaced it with these two force components, you can see that we have an AB going in the y direction and we have an AB value going in the x direction, plus also an AE value. So that means that resolving forces in the y direction only is a sensible thing to do, because you're only going to pick up the AB value. Okay. What you want to do, and sometimes I skip this step because I'm happy with this diagram, so sometimes I skip this step. But the next thing to do, at least in the course notes, next thing to do is to split up the AB, and so then draw a new force diagram. You are starting to draw a lot of free body diagrams each time. There's a disadvantage with that. So either maybe you might want to stick with this diagram, or you move on to a new diagram. You probably will want to draw a little sketch of the geometry to the side of your solution, just so that you know what you're going to define as an angle. So I'm going to call that theta. And then on your little triangle geometry here, you put some lengths on, or the ratio of lengths, or whatever it might be, so that you can then think about the trig equations. So here we've got, on the next bit, we can say that cos theta is the adjacent divided by the hypotenuse. So that's going to be 4 divided by 5. And sine theta is going to be the opposite divided by the hypotenuse. So that will be 3 over 5. Alternatively, some people like to use the actual theta values in their trig functions, in which case you probably would use maybe one of these functions to find theta, or maybe you might use your arctan value of theta, where you're doing the opposite over the adjacent. Okay, so that's going to be the 3 over the 4. Whoops, no, sorry, that's tan theta. I saw a student make that mistake this week, that's why it's in my brain. So that's tan theta, and then to find theta, I will then apply arctan theta to 3 over 4. Provided your calculator is set to degrees, you will then get, for that particular case, 36.7 degrees. So there we've got that value down there. So some students like to use that value and then substitute it back in to these two terms here and here. So you play with your geometry. Maybe you're going to split up your AB and create a new free body diagram. As I said, I tend to skip that step. Certainly you will want to play with the geometry and decide either what cos theta is going to be, and sine theta, or sometimes even I might even work out what that angle is there, and I call it a gamma, and work out what cos gamma is. So you have to use your best intuition of what is going to be the best way to approach this problem. Okay, so moving on. The approach on the left is where we've now replaced the sine theta with 3/5 and the cos theta with 4/5. This is the preferable approach to use, if you can cope with it, because you're not going to get truncation errors in your solution. If you work out the angles, you can substitute them in here, and then just make a note of them. So note we've got this force here going in the x direction, plus also this force here. Okay. So the approach on the left, when it's now sum up forces in the x direction, so the book is kind of taking this for a template approach. Always sum up in the x direction, always sum up in the y direction. Would have been advantageous to do that first. So sum up the forces in the x direction. What have I got? I've got 4/5 AB plus AE, and then I've got this external force, which is a reaction force of minus 80. It's going in the opposite direction, so it's a minus. Okay, so I can't do much with this equation other than call it something. So I call it equation 1. Then I'm going to sum up the forces in the y direction. So I've got 3/5 AB going in the y direction. And then what we got? We got this going in the negative y direction. So we've got this term and this term. Okay. Rearrange this, and that will give us that AB is 5.5. Notice the value is positive, and when it's positive, that means we're in tension. Okay. Then I can go back and substitute the equation back into equation 1. So I've found what AB is. So I can substitute that back into the AB value, rearrange this to find AE, and then we find that AE is plus 75, so it's also in tension 0.56. So the approach on the right is doing the same thing really, but in this case, instead of using, we've dropped the cos theta, we replaced it with 4/5, and here we've got cos theta, and theta happens to be 36.87 degrees, which is only true to 5 degrees, I think. So the disadvantage with this approach is that you are likely to lead to truncation error. You need to, once you finish the joint, you need to go back to your original framework and then decide which joint you can go to. If I went to joint E, let's say if I'm trying to solve all joints here. If I went to joint E, I now know what this internal force is. But this one here is unknown, that's unknown, and that's unknown. So we've got 3 unknowns that I'm cutting through. But if I go to joint B, this force is now known. I now know what AB is. So if I cut round B, well, that's unknown and that's unknown. So I only have 2 unknowns if I cut round B. So there's only one place where I can take my next joint, unless of course I go back to joint D again, which I'm not interested in. So the next stage is to move on to your next joint, and in this particular case we can see that that's going to be joint B. So we're going to start at joint B here, and when I do my free body diagram for joint B, I want to put in where the theta is. So I've worked what that is using complementary angle. So I've got theta in this side. So draw a little z. So that means we've got theta on that side. So that worked out. And then I draw any forces I can see. I've got a horizontal construction line there. And we've got AB going off in this direction. So notice we've just flipped AB. So it's the same AB value, just flipped in the opposite direction. We've got BE going in this direction and BC going in this direction. The other thing, notice that although I previously worked out what AB is, on my first diagram I don't substitute the value in. That's a big mistake, because this diagram here could earn you method marks, assuming that you might have gone wrong on this value here. So do a free body diagram, and at the moment don't substitute in the value of AB. Okay, so what do we do next? Well, we do the same procedure as before, where we're going to split up the AB force into its components. So we're swinging through theta here. So that means we've got AB times cos theta. And the other one we're not swinging through, so that's a sin, which means it's a sine. It's a sin not to swing through. Okay, so that split up our AB into its trig. The trig hasn't changed, I think. We've still got cos theta equals 4/5, because I've been good. I've used the same theta here, definition of the same theta is here. And sine theta is 3/5. So it's quite straightforward. So going for the bit on the left, I'm now going to replace my cos theta with a 4/5. And my sine theta with 3/5. Okay. This case again, it would have been better to resolve in the y direction, but nonetheless in the textbook they resolve in the x direction here. So we've got AB. Now notice that AB is pointing right to left, which means we must have a negative AB. And this is another reason why not to substitute your values into too early, because sometimes you can confuse yourself about double negatives at the initial stage. So just think of AB pointing this direction. Whether AB's value is actually positive or negative, we ignore when we're doing this. Okay. So I'm not making any. I'm not referring back to whether I know which way AB is supposed to be pointing. I'm going to let the minus signs help me out and work out my solution for me. Then I've got BC pointing left to right. Let's rearrange this. Actually, sorry, I'll take this all back. Resolving in the x or y direction makes no difference. Apologies. So rearrange this, and we've got AB now pointing. We've got BC equals 4/5 AB. Now, when we're at this stage, kind of like the final stage, that's the stage when you want to substitute in the AB value. Substitute in the AB value, I end up with a positive value, and then I know that's going to be in tension. So I'm not going to go over it, but alternatively you could use the angle approach. I wouldn't recommend it. When I resolve in the y direction, what do I get? Okay, so this is another example where I would probably deviate from the course notes. If I was resolving the y direction, personally speaking, I would resolve downwards. Okay, there's no reason why you have to resolve upwards. The advantage of resolving downwards is that we end up with positive numbers, both pointing downwards. if we're going to stick with our convention that up is positive, then it's a bit stupid because we've got nothing pointing up. So we've just introduced minus signs to confuse us. So we've ended up with a minus sign here and a minus sign here. So if I redefine downwards as positive, I would have had a positive sign and a positive sign, which I think is easier to deal with in terms of algebra. So we're looking for BE, so take AB over to the right hand side. That gives us a negative 3/5. And we're going to substitute in the AB value, and then that leaves us with a negative BE value. So since it's a negative value, we can state that it's in compression. For shorthand for in compression, you can just write a C next to it. Shorthand for its in tension, you can just write a big T next to it. Okay, so where are we going next? So we've done A, we've done B. Can we move to C? Well, if we move to C, we know what this joint is now, and we know what this joint is now. So move to C, you can see I'm going to be cutting through 3 unknowns, so I can't. So the only choice that I can move to is to move to E and cut through its members. I know this joint now, internal force in that member, and I know the internal force in that member. When I cut through, I'll only be exposing 2 unknowns I don't know. So I've got no option but to go to E next. So here we are at E. So again, the first 3 body diagram I do is just using the variables of the joints. So me personally, I would be doing this as CE, but because they've chosen it to be E, they've called it an EC. So that doesn't really matter. Both are valid. They're just names. So and names relating to the joints, so you make sure that you know which member you're dealing with. Okay, so I name them, and then if there's any angles I can stick on my my graph, I'm keeping theta consistent throughout my process. Good plan. Don't have to, but it's a good plan. And then that means each time I do my triangle, I'm going to get the same result for cos theta and for sine theta. So that's a good plan. So the next thing that you can see that you need to do is to split up the EC value into 2 components. So swing through the angle, that gives us EC is times cos theta. Do the opposite, don't swing through it, that's a sin, so that's EC sine theta. Okay, so previously we solved these before. So I can then substitute cos theta and sine theta into my diagram, get rid of them, and then I'm in a position to resolve in a particular direction. I don't know whether resolving in the y direction would be better or not here. So in the y direction, do we know BE? Yeah, we know BE, don't we? Seems to recall. Yeah, we know BE and we know AE. So if I know BE and AE, actually it seems to suggest to me that resolving in the y directions would be the good thing to do first. Nonetheless, in the course notes they resolve in the x direction first. So what we've got the 4/5 EC pointing off left to right. We've got the EF pointing off left to right, and then we've got AE pointing right to left, so that we need to put a negative there. I know the value AE, so I'm going to introduce that into my equation now after I've established this line. And then not much else I can do but move on. So there's the alternative approach if you're going to use angles. Okay, last page. So here, if we now resolve upwards, resolving upwards is actually a good plan to do. Got positive numbers on the left-hand side. So I'm resolving these two values upwards, so that just can leave me with BE plus 3/5 EC. That's it. So just rearrange this to find out what EC is. That's the thing I'm interested in. After you've rearranged and done your transposition that you're happy with, you then substitute in your value. So that avoids minus values, so I know that's supposed to be a positive, so if you leave it to the end. So that gives me EC equals this value here. Okay. Then you can go back to the previous equation. What was the previous equation? Which is that we've got these two unknowns here, EC plus EF. And here we have the EC value, which we've just found from the previous equation. So I can substitute that in, rearrange it to find EF, and then state EF is a positive, and therefore it's going to be in tension. Okay, so that's talking through the notes. The next example, example B, I will just be writing on the whiteboard.